We'll start. Today we'll continue to talk about waves. Let me move this thing here so I can see it a bit easier. Rearrange. Everybody can see the slides and hear me? Type 1 if you can see the slides and hear my... Okay, perfect. Okay, just a quick check. We continue to talk about waves in the ocean. And in last class, let's do a quick review from last class. Last class, we talked about more general about waves, some wave parameters, and the most important one is the wave dispersion relationship. If there's only one equation you want to remember, I probably suggest remember this one. This is the more general form for different kinds of waves, either deep water wave or shallow water waves. This one both works. Get this pointer. This one both works. And depends on the condition you have. If it's deep water, you know this h goes to infinity. You can think that h goes to infinity, and you can further simplify this. If this goes to infinity, this tanh infinity goes to 1. And that will give us like omega equals to gk. And you can further figure out c equals to this number, or c equals to, because c just equals to omega divided by k, right? So you can figure out c equals to square root g over k in this case. But it's if it's for shallow water, you know this h is very, very small. So tanh kh will approximate to kh. In that case, you get this one, and you move this thing here, square root. You know that the speed is the square root of gh. So this one is g over k. This one is gh. So this depends on the wavelengths of the wavelengths that of the wave. But this one is no longer depends on any wave properties. It depends on the just simply depends on the water depth. So that's how shallow wave works. If the water depth is deeper, it will propagate faster. If shallower, it will propagate slower, as long as they are categorized as like shallow water waves. So for oceanographer, we usually use these two numbers. If h is longer than half of the wavelength, you can consider this as deep water wave. If it's shallower than 1/20 wavelengths, we consider as a shallow water wave. So this is kind of thing you probably will come in handy in some point. And after that, we talk about one of the most common surface wave. It's wind-driven ocean waves. Some people call it wind-driven sea surface waves. So this type of wind are generated by this type of waves are generated by wind or storms, that atmosphere disturbance. And a few important parameters here is the fetch, is the distance, how long the wind blows, and also the duration is how long in time. Okay, fetch is in space, and duration is how long time this wind blows. And of course, if you got higher speed, you will have larger waves. So all these three parameters contribute to the wave height, surface wave height. And they are for a lifespan of the waves, there are different kind of areas. When it's still in the fetch, these are seas, like very highly irregular, highly interference waves. When it propagates further, we know waves dispersive So longer wavelengths will travel faster, and like smaller wavelengths will travel like slower. So waves start to kind of have different speed. Some guys travel faster, some guys slower. So we can kind of see very regular waves. These are ocean swells. When it get to the coastline, when the water depths become shallower and shallower, what happened is the wave height will increase, but the wave will slow down because the h becomes smaller. Remember the previous equation, when h gets smaller, the wave speed also gets smaller. So, and then because the wave height keep growing, there is a chance that it's going to break. We have different type of breakers, but anyway, it's going to break. So that's kind of the general idea of waves in the ocean. And we talk about there are different type of mechanism generating waves: the winds, the tide, the tidal forcing, and there is the other one is underwater disturbance. So that disturbance is what we are going to talk about today. It has the name called Tsunami. So this is kind of the way we are talking about. So I look at Wikipedia. So this is what they mentioned. The definition for tsunami is a long, high sea wave caused by an earthquake, submarine landslide, or other disturbance. Anyway, it's kind of some activity happens on the seafloor or underground that can all causes this tsunami. So usually these, when there's an earthquake or a landslide, usually they release a lot of energy, quite a lot of energy at a very short amount of time. So this disturbance, think about that, this disturbance will cause that the sea level probably will cause disturbance in the ocean, and that disturbance will propagate to the surface and increase the kind of the surface water. Once they are increased, the gravity starts to act on that. Gravity trying to pull it back, and when it pull too much, it will keep bouncing again and again. So this wave will propagate. Once there is an earthquake, this create this water bulb, and it just keep propagating out. So for this type of wave, because sometimes they can get very big amplitude, so they can be like non-linear. They are not always linear, so they can be like non-linear waves. So the wave height can get very big wave height, and they are not dispersive because their wavelength is very, very long. In this case, the wavelength is probably a few hundred kilometers, but consider like compared to our like 4,600 meter water depth. So this wavelength is way too much. So this is definitely shallow water wave. So for a shallow water wave, they are non-dispersive. They kind of travel at the same speed. For different frequencies, they are travel at the same speed. But in the open ocean, the tsunami, you don't really see it because the amplitude is not that high. But when it gets close to the coastal area, this amplitude significantly increase. So the tsunami is a Japanese. So now I think it means harbor waves. So it means when it only seen in the harbor or inside the coastline. So what happens, you see nothing there, but suddenly it just appear. Because when we know that when we get to the coastal area, the water depths get shallower and shallower. So those big waters start piling up, and they have nowhere to go. They have to pile up like in height. So they increase in height. And because there are a lot of energy, there are a lot of water in there, it kind of creates this kind of like wall, like a few meters, like more than 10 meters. In the history, I think the tsunami is much bigger. Let's see that. So this tsunami. Okay, so this is the generation of tsunami. One example here. So this is slump, like the underwater seafloor slide or something like that. Once they have this slump, it releases energy, and that energy will perturbate the water. So the surface can feel that perturbation and start to evaporate. Not evaporate, start to vibrate. So this is the example of a tsunami occurred in April 1st, 1946. So, for instance, there is an earthquake in this region that will cause the tsunami and propagates for a very, very long distance. So I think this is around Alaska. And here they have different lines. So 1 hour later, so 2 hour, 3 hour, 4 hour, 5 hour. So within 5 hours, it reached the Hawaii. So you can see the speed for tsunami is really quick. Okay, I think I already slightly covered this. So for tsunami, we have to consider that as shallow water waves. So shallow water wave, the speed GH, square root of GH. So from previous slides, it's in Pacific. And let's check the depths for Pacific. Around that region, it's about 4,600 meters. And you input this here, you calculate everything, and the speed is like 212 meter per second. So that's very quick, like half of the sound speed. So it's very quick. So you can see that's why it traveled from Alaska to Hawaii only 5 hours. Because the shallow water wave, it has to be very quick. Because in the deep ocean, I mean like in the open ocean, the water depth is much larger. So shallow water wave there has to be traveled very fast, very scary. This is another example. It's 2004 Indian Ocean tsunami. So that one is a big disaster for a lot of coastal areas. I think these yellow countries that shows that the country get affected by this tsunami. So it can affect for a very large range, not just India and around like Asia. They can also affect Africa. See here. So they have big impacts and kind of a big disaster. Can be globally. This is a few pictures about that tsunami. And when the big wave come to the land, they dissipate a lot of energy and kind of destroyed everything. And they also bring ship to the land, because those are big waves, they push the ship. So it's caused a lot of damage. So this is another one. I think this is just right after the wave coming, and there's still water in here, flooding. So this is this is in another tsunami. So this is the Honshu tsunami 2011. This is in Japan. Similar thing, it just appear and it bring quite a lot of water because the wave height is so large. Most of the dam or most of the barrier we create for this sea level rise and falls was not high enough for tsunami, because this suddenly some energy piling up. We didn't expect that. So they kind of just flood in and destroy everything. Yeah, this water just get over this pump here, come to destroy everything. So pretty scary. The same here, the ship even though these are kind of bigger ship, but still they are carried away by tsunami. I have find a very good TED talk, like TED education talk about the tsunami. So I'm going to play that. Let me see.
In 479 BC, when Persian soldiers besieged the Greek city of Potidaea, the tide retreated much farther than usual, leaving a convenient invasion route. But this wasn't a stroke of luck. Before they had crossed halfway, the water returned in a wave higher than anyone had ever seen, drowning the attackers. The Potidaeans believed they had been saved by the wrath of Poseidon, but what really saved them was likely the same phenomenon that has destroyed countless others, a tsunami. Although tsunamis are commonly known as tidal waves, they're actually unrelated to the tidal activity caused by the gravitational forces of the sun and moon. In many ways, tsunamis are just larger versions of regular waves. They have a trough and a crest, and consist not of moving water, but the movement of energy through water. The difference is in where this energy comes from. For normal ocean waves, it comes from wind. Because this only affects the surface, the waves are limited in size and speed. But tsunamis are caused by energy originating underwater, from a volcanic eruption, a submarine landslide, or most commonly, an earthquake on the ocean floor, caused when the tectonic plates of the Earth's surface slip, releasing a massive amount of energy into the water. This energy travels up to the surface, displacing water and raising it above the normal sea level. But gravity pulls it back down, which makes the energy ripple outwards horizontally. Thus, the tsunami is born, moving at over 500 miles per hour. When it's far from shore, a tsunami can be barely detectable, since it moves through the entire depth of the water. But when it reaches shallow water, something called wave shoaling occurs. Because there is less water to move through, this still massive amount of energy is compressed. The wave's speed slows down while its height rises to as much as 100 feet. The word tsunami, Japanese for harbor wave, comes from the fact that it only seems to appear near the coast. If the trough of a tsunami reaches shore first, the water will withdraw farther than normal before the wave hits, which can be misleadingly dangerous. A tsunami will not only drown people near the coast, but level buildings and trees for a mile inland or more, especially in low-lying areas. As if that weren't enough, the water then retreats, dragging with it the newly created debris and anything or anyone unfortunate enough to be caught in its path. The 2004 Indian Ocean tsunami was one of the deadliest natural disasters in history, killing over 200,000 people throughout South Asia. So how can we protect ourselves against this destructive force of nature? People in some areas have attempted to stop tsunamis with seawalls, floodgates, and channels to divert the water. But these are not always effective. In 2011, a tsunami surpassed the flood wall protecting Japan's Fukushima power plant, causing a nuclear disaster in addition to claiming over 18,000 lives. Many scientists and policymakers are instead focusing on early detection, monitoring underwater pressure and seismic activity, and establishing global communication networks for quickly distributing alerts. When nature is too powerful to stop, the safest course is to get out of its way.
Yep. So this tsunami, so next time, I hope we don't run into any tsunami, but if we run into one, just get out of there as quickly as possible. It's really deadly. Okay, so we're going to continue to move on. So I think for those part, we finished all the surface waves, the tides, the tsunami, also the wind-driven surface wave, and the most common one we've seen in our daily life. From now on, we're going to move a little bit, talk a little bit about the internal wave. These are the wave we less know. Even for scientists, it's less known because they are not easily observed as a surface wave because they are under the water, right? But they exist. And scientists predict the existence of internal wave very long time ago. But to get proved, to really prove it exists, it's kind of recently thing. So this is how they think at the beginning. So when they observe this is density profile, so this is density as a function of depth, and when they observe the density profile, they find this. So for the surface water, the density is kind of not that dense, but if you increase the depth, the density increase significantly, and there's at some point there's a density increase like dramatically, the area dramatically, and we tell that's called pycnocline. So that's for density quickly increasing. So think about this. So this is kind of, if this is layer 1, this is layer 2, this is kind of intermediate layer between layer 1 and layer 2. Think about our surface wave. It's the interface between the air and water. They have different density. So if you think there is an interface wave at the surface, there should be another interfacial waves around this area, because this, you can also think this as an interface between two different medium. So this is how they think there could be some internal waves. But later on, they prove it is true. We got observed internal waves, and we can see some surface signature of the internal wave. But basically, the idea for internal wave is just the stratification in the ocean, or the different layering of the ocean. We can have wave propagates for different layers. So this kind of give you another view of the internal wave. Think about this is a more simplified model or scenario here. We only have two medium here, row 1 and row 2, and we forget about that picnocline. So we think that picnocline is pretty thin, or in some cases it's just 2-layer. And for this 2-layer water or 2-layer any fluid, we can have an internal wave propagating at the interface. Think about row 1, row 2. So there's another layer of air here, but we are thinking about the fluids here. So we have one layer row 1, the other layer row 2. And if you start to perturbate it, we can do this in the lab. So if you have two different type of fluid, they have different density, oil and water, for instance, and you dye the water with different colors so that you can easily see. You somehow perturbate it, you can see the interface start to propagate, that behave like waves. Usually, if we do that, very interesting is that those waves kind of in slow motion. I couldn't find proper video for that, but I just describe you. So if you disturb that, they can like have very big wave high, but they kind of propagates very slow. So we kind of perturbate very, very slow, kind of in slow motion. That means usually the wave speed is slow. Why the wave speed is slow? So we don't derive this, but to give you guys an example, so the internal wave speed is calculated from this equation. So this is square root g over k, and then something related to the density of medium 1 and 2, the different medium. And to be more precise, it depends on the difference of the medium. Think about this. If row 1 and row 2, there's no difference. If they just all water, they should have, should get the same wave speed, just regular surface wave, right? So that depends on the difference. Rho, so in this case is the lowercase density minus the first layer density, and then also divided the density, the sum of the two density. Let's do a quick check here. So if you think about this, rho 1 is very, very small, like very close to air or something, it should become surface wave. So if this is very small, everything here, so rho 1 kind of just compared to this guy, rho 1 is too small, so this is only rho 2 left. It will become rho 2 over rho 2, it will become 1. So C will going to be square root of G over K. And we know that square root G over K, this is exactly the same as for our surface water waves. When there's no density difference. So that's for shallow water wave. Let's kind of give you a quick check about the speed of internal wave. Because, and let's do a bit more realistic example. There are two medium here, and rho 1 is smaller than rho 2. say we have water. One density is 1025, the other is 1035 or something. So when you input everything to the equation here, you will have 1035 minus 1032, so it left 10. 1035, 1025, so you plus this, like a 2 something. So you need to, you kind of have the surface wave speed, but get time a ratio, like very, very small ratio. So this is why this C kind of decreased quite a lot. So we can see the slow, very slow motion of waves, interfacial wave for internal wave. So these waves, they are kind of in slow motion. So they usually have a longer time scale than the surface wave. And they can also have a bigger spatial scale if it's internal waves. So this is the internal wave seen from the space. They are not, so for this ripples here, they are not the wave, they are not showing the wavelengths of the internal wave. They're showing the surface signature of the internal wave. Because the internal wave, they are happen in the interfacial region. You cannot see that from the surface. Even though the surface is flat, you can still have internal wave propagating under that. There's no problem about that. For the reason they see this surface signature, it's kind of a more complicated mechanism. For the surface, when the internal wave is propagating, they create very small ripples at the surface. Usually that ripple is not easy to see by radar, like by eyes, but they have a phenomenon, the wave scattering phenomenon called, what's that called? I kind of forget. So because they are surface ripple on the surface, when the wave coming for a few different frequencies, particular frequency, some wave can get enhanced, some wave can get kind of destructive. So for that case, you kind of enhance the view. And we see this light dark pattern for the surface. So that's kind of tell us a message. There are surface ripple there that create by internal wave. And you compare with the geographic location, it's a location that usually generate internal wave. You can kind of figure out that's for internal wave. So usually internal wave generate during the continental slope area or somewhere seafloor topography have big change. So this is, I think this image is from Gibraltar Strait. So probably this is a narrow strait. When the tide flowing in and out, the water have to converge, and because their topography there, they kind of more likely to when the water coming in and coming out. For instance, think about this: if there's a mountain, the water, if the water want to come in, it has to go above the mountain and then come back again. So that motion will keep propagating and generate internal wave, something like this. So usually internal wave are generated in underwater topography. It's more complex area. Let's see. So this is another photo of the internal wave surface signature. So this is signature I talk about. You usually see a bright line and also a dark line. So light dark area, and they are propagates very irregularly. So this is kind of the surface signature of internal waves. And this is the underwater observation. I think this is for acoustic backscattering, if I'm not mistaken. So this is kind of what you see from the surface. You have an ocean, and you see this surface signature of internal wave, and you have a ship here doing the experiment, collecting the data. And one way to see internal waves using acoustics, backscattering. For different layer of water, because they have different density, they have different sound speed, so they can have different acoustic impedance. And that impedance will decide how much energy, acoustic energy, get reflected back. So we collect that acoustic data, we can somehow know the layer of the water. So if the ship, I don't know which direction it travels, say if it travel, I think it's travel this way. Probably take an example during this course. And what it see is that, okay, there is a surface area kind of more acoustic impedance or more scattering. And that area, it's kind of, okay, I think I'm wrong. This is probably not acoustic scattering. I'm not sure about what that is, but from this figure, but I don't think it's acoustic scattering. But this part looks like acoustic scattering. But anyway, the main message here is that you can kind of see a lot of waves. A lot of waves in the water, although the surface is pretty calm. So this is kind of how they observe internal wave. I know when they study internal wave, there are a lot of acoustic people studying that for two reasons. One reason is acoustics is an effective tool to study internal wave. It's much more convenient than using traditional physical oceanography like CTD. If you want to capture this quick evolution of internal wave, it's kind of hard. So for one reason, acoustic is an effective tool, that's for sure. The other reason is acoustic people care about internal waves. Because propagation, if they're doing underwater survey, they are very interested in how the internal waves will affect the sound propagation in the water. And also a lot of Navy care about internal waves because they have submarine there. And if you send submarine around this interfacial media here, and there's internal wave coming and start to perturbate this can be like have a lot of impact for less submarine. It means that in one case you are coming into a very dense area. In the other case, you are coming into a much lighter area. So if you suddenly come to a lighter area, it can suddenly how to say that? So the submarine will quickly flow to the surface, or like quickly decrease, fall into like a deeper depth. It depends on which layer you are coming from. So that can be scary for submarines. That's not good for them. So they also care about internal waves. So nowadays there are a lot of people studying internal waves, but as I say, they are kind of subsurface. It's not that much to understand. And there are still a lot of things we don't know about internal waves. And I think in next week, we will have a colloquium speaker talking about a full lecture of the internal waves. So I think he will cover more about that, but I will just give you a basic idea. So this is kind of modeling or kind of giving an idea what it looks like for internal waves. Oh, why it's not? So usually when there's a complex seafloor topography and the tidal forcing or the water coming through can generate a lot of perturbation in internal waves. And that way it can propagate. So this area is usually the generation of internal waves. And this is kind of the idea from the surface. After it generates, it propagates kind of in different directions. Yeah, so this is kind of the idea of internal wave. And this is kind of tell you how the internal wave is related to the vertical density profile. Usually we know when we have the, if you go deeper, we will have larger density. That's the kind of the normal case, the stratification case. So there are three cases here. It depends on this vertical density gradient is larger than 1, or equal than 1, or smaller than 1. If it's equal than 1, we know there are probably no perturbation. Okay, the idea is here. There are two layers of water. One is, right now we're thinking about they have different densities. If let's think about like a normal case, like a stable case. So that means the light water is on top, the heavy water is below. In this case, if you raise the water particle, because the water particles originally here, you raise it up, it will be too heavy for the light layer, so it has to sink down. But once it sinks down, compared to the dense layer, it's too light for it, so it has to bounce back. So the water particle has to kind of bounce back and forth. So this is how it related to this rho dz here, because it depends on that. So that's the case. I think that's the case for this stable case. The rho dz is smaller than 0, because z right now it defines as pointing up. Anyway, so this is that stable case. For unstable cases like this, so we have heavier water on top, lighter water on the bottom. In this case, if you raise a water particle in between, it will just keep going up, and eventually all the light water and deep water, they kind of want to flip around, and they are not stable. So this is an unstable case. And if there's no density difference, it's a neutral case, kind of basic. So one important concept about this internal wave is the buoyancy frequency. Okay, I think I run out of time. I'll be a bit quick here. So this is the buoyancy frequency. It comes from, okay, I'll skip where it comes from. It's this form. It's only related to this is the vertical density gradient, and also the gravity and the density of the water. So I think I will leave this to next class so that I don't need to hurry up. Okay, I think I will end it here today. So I will leave this to next class. But I have a wave documentary will show for this class, but it's already recorded. It's a documentary. It's an old film. So I think I will just send you the link and let you guys watch it. I think it's about 35 minutes long. It's almost a class. So I think I will skip one class, but you guys need to watch that documentary, because it explains how the early scientists work on the waves. And even though the technique is kind of very old there, but they still it's still very we still need to see that, because they do really true science, and we still use the knowledge they get from those data. So it's a very good documentary. I see that documentary when I was studying oceanography in University of Delaware. So that's the only documentary they show. So I would like to show you that. So we will skip one class. I don't know which one yet. I will email you guys. We'll skip one class, but you have to watch that documentary. And I will send you the link at some point. Okay. Sorry for the delay. I think I will stop it for now. If you guys have questions, you can shoot it out. If not, I will see you in next class.